Log on, tune in, find out. Another good idea from Cambridge.
Quiver presentations of descent algebras of finite factors.
Thank you. Yeah, it's a pleasure to be here. And yeah, I want to talk about these Quiver presentations. Descent algebras are subalgebras of the group algebra of a finite Coxeter group. They've been discovered by Louis Solomon in 1976. And they provide a natural explanation for a formula that he proved actually 10 years earlier, which expresses the sign character of the Coxeter group in terms of permutation characters on parabolic subgroups. It's an interesting object to study in its own right. It has nice properties, but it also arises in surprising places in applications. Recently, in the theory of random walks on hyperplane arrangements, where, for example, this famous calculation that it suffices to shuffle a deck of cards 7 times to bring it in random order is a special case, special application of a problem that can be formulated in terms of these descent algebras. These algebras are well studied, but in general no presentation of them is known. What's even worse is it's sort of obvious that such an algebra is a basic algebra, and as such it should have a presentation as a quiver with relations. Until recently there was not much known about quivers or relations for these algebras. The one thing that was known is the structure of the quiver in the type A case, the symmetric group case, which is of course related to the partitions of N, and Garcia and Reutenauer have in 1989 described this quiver as some sort of restricted partition refinement. But after that, not much. In relation to the hyperplane arrangements and the random walks on them, the algebra has received more attention. There's a related algebra, the phase monoid algebra, that goes with the hyperplane arrangements, which on the one hand has a nice presentation as a quiver with relations, and on the other hand contains a copy of the descent algebra. And so there has been some hope of getting presentations for the quiver, for the descent algebra from there. The approach that I'm going to present here is different from that, and as you will see, completely elementary. So to start from the beginning, let W be a Coxeter group. That's a group with a particular relation, Coxeter generators, set called S, and the generators little s little t, relations which basically give the orders of products of 2 of the generators, and the generators themselves are involutions, as for example a symmetric group generated by these basic transpositions, or dihedral groups generated by 2 involutions whose product has order m. These groups have a natural length function with respect to this presentation, a length function which has the nice property that the length is very much under control. It only changes by 1 if you multiply a generator to a word. I will assume that the Coxeter group W is finite, then it has a longest element in terms of this length function. The descent algebra is defined in terms of parabolic subgroups, in terms of standard parabolic subgroups and their distinguished coset representatives. For each subset J of the generating set S, you have such a standard parabolic subgroup generated by that subset. It's a Coxeter group in its own right, and it has a nice set of coset representatives, which I call capital X subscript J, described by the fact that it consists of all elements of the group which become longer if you multiply them on the left with a generator of the subgroup. It's a right transversal of the parabolic subgroup, and it consists of the unique elements of minimal length in each coset. Due to the presentation, due to the fact that the generators have order 2, of course, if you take the inverses of these elements, you get a left transversal, and then there are a couple of other sets that are closely related. If you have 2 subsets of generators, if you have a chain of parabolics, then of course intersecting the coset representatives with another parabolic subgroup gives you a set of coset representatives of the small subgroup in the bigger one. And if you have 2 subsets, the intersection of a right transversal of the one and a left transversal of the other gives you a set of minimal length double coset representatives of the 2. So the big group is partitioned into double cosets, and the double coset representatives can be taken out of this intersection, which I will call capital X subscript J and K. While we're looking at them, there's a nice and important theorem which says that the intersection of any 2 parabolic subgroups is a parabolic subgroup, or more precisely, if you take the conjugate of a Wj by a double coset representative D and intersect it with Wk, then you get a standard parabolic Wl, where L is precisely the D conjugate of J with K. And it's this type of conjugation that will play a special role later. Continuing this theme, and as a preparation for the statement of Solomon's theorem, I want to partition the set of double coset representatives X, J, K into subsets according to what this intersection J conjugate by D with K is. And I call the resulting set X, J, K, L. It consists of all those double coset representatives in X, J, K, which have the property that if you conjugate J by it and intersect with K, you get L. One more piece of notation. Little xj is the sum over capital Xj, or rather capital Xj inverse, inside the group algebra. And I don't care too much about the underlying field. We let it be the rationals. So it's the group algebra over the rationals. Little xj is the sum of over the left transversal for Wj inside the group algebra. Solomon's theorem then says if you multiply 2 of these together, I take the I take the sum over the elements in this set. So little xj is a sum of left coset representatives of all left coset representatives inside the group algebra. And Solomon's theorem then says if you multiply 2 of them, the result decomposes as a linear combination of such things, and the structure constants A, J, K, L happen to be just the sizes, just the sizes of these sets capital X, J, K, L. So this describes the algebra. So this says the subspace generated by the little xj's as a subspace inside the group algebra is in fact a subalgebra. and the structure constants are closely related to the parabolic subgroups. There's a bit more. If one considers the map, let's call it theta, which associates to j or little xj the permutation character of the Coxeter group W on the cosets of the parabolic Wj, then this map extends to an algebra homomorphism between the descent algebra and whatever the image of theta in the character ring is. And this means that the product of two such permutation characters, if you multiply two of them together, you get the same structure constants. If you look at this map more closely, then of course the image of this map lies inside the character ring. It might be a proper subring of the character ring, but the character ring is a commutative algebra, and so the image must be commutative. Also, Solomon shows that the kernel of this map is generated by differences of xj's and xk's, where j and k are conjugates of each other under the conjugation action inside the group. This is nilpotent, and it coincides with the radical of the algebra. From this one concludes then that the descent algebra sigma of W, and this is sigma of W. That's the symbol used for the descent algebra, rather than the sum over a set capital Xj inverse, which is the sum over all the elements. From these two properties, one concludes that the descent algebra is a basic algebra, an algebra whose irreducible representations are all one-dimensional, such it must have a presentation as a quiver with relations, and the task here is to find it. Why descent algebra? Well, there's a slightly different way to look at this. If one defines the descent set of an element in the group as the set of all generators, which make it shorter when you multiply the generator from the left, then you can partition the entire group into descent classes, 2 to the n of them, if n is the size of the generating set. And you can describe the descent classes as inverse images of subsets of generators. Actually, here it's complements of subsets of generators. It's the complement of the subset, which is the descent set, that serves as a label on the descent class, which are called capital Y subscript something, rather than capital X subscript something. Extreme examples of such descent classes then are Y subscript S. That's all elements whose descent set is the complement of S in itself. That's only the identity. And at the other end of the spectrum, one has Y empty set consisting only of the longest element. Clearly, since the condition on the minimal length coset representatives can be formulated in terms of descent sets, namely, one can describe the right transversal of Wj as all those elements W which have the property that their descent set avoids J entirely. Each such capital Xj is a disjoint union of capital Y k's, and exactly those k's which contain J. And then if we form elements little yk in the same way as we formed elements little xj earlier, then one sees, since this comes from a disjoint union, from a partition of the entire group, they form a basis of the subalgebra that we're looking at. And so from this point of view, it's easy to see that the xj's also form a basis, and that the dimension of the algebra in question is 2 to the n. There are formulas relating the little x's to the little y's. Since x's are disjoint unions of y's, the little x's are sums of y's, and by Möbius inversion you can express y's as sums of little j's up to a sign. In particular, W0, which is the sum inside the group algebra over the set y subscript empty set, then can be expressed as the alternating sum over all xj's, and under the homomorphism theta, what is associated to W0 is the sign character of W, and in this way it's expressed as a linear combination of permutation characters. But that's just a side remark. To get a feeling for how these things, the sums of coset representatives behave, it's sometimes useful to have a graphical representation of them. Here one can use intervals in the Weak-Bruha order, or represent these sets as coset graphs, as directed colored graphs, where you take the elements in the set as vertices, and as edges then you take the elements generators which produce one coset representative from another. For example, the symmetric group on 5 points sitting inside the symmetric group on 6 points, generated by 5 generators, gives rise to a straight line where the 6 vertices in this graph are the 6 points permuted by the symmetric group on the 6 points. More complicated examples arise when you consider other situations. For example, a direct product of 2 symmetric groups in a larger symmetric group gives rise to a structure like this. Some properties of these sets of coset representatives can be nicely illustrated in terms of these graphs. For example, the transitivity along a chain of parabolic subgroups, J inside K inside S. One can decompose the big set of coset representatives of the small group in the entire group as a product, obviously. The dot here in the between them indicates that this decomposition is compatible with the length function, and in terms of the coset graphs, this gives such a sort of semi-direct product of 2 coset graphs, where you have one ingredient is the coset graph of the symmetric group on 3 points inside the symmetric group on 4 points, and up here symmetric group on 4 points inside the symmetric group on 5 points, and then you take the rectangles spanned by them and complete it according to the presentation of the group to a full rectangle. Another property, shift property, is concerned with conjugate subsets. Here in the special situation where we take 2 subsets J and K of S, then we can look at, with regard to one double coset representative D, we can look at the intersections J conjugate by D intersected with K, and J intersected with the conjugate of K by the inverse of D. And the property is that the graphs basically look the same, except that the vertex corresponding to the identity is shifted by this double coset representative. Third property is a Mackey decomposition, which Mackey decompositions do are concerned with two subsets, two parabolic subgroups, and then one can decompose the transversal with respect to one subgroup in relation to the other as a disjoint union of such shifted coset graphs, and the disjoint union again is indexed by the double coset representatives. In terms of the picture, in terms of the coset graphs, this means that you start with the big coset graph, this example we've seen before, and then when you want to decompose it with respect to another subset K, then you throw out of this coset graph all the edges which don't have colors that occur in K. And the formula says then the graph falls apart into connected components, which themselves are coset graphs sitting in a smaller subgroup. These three properties together can be used to give a one-line proof of Solomon's formula, which establishes the existence of the descent algebra. One can use the Mackey decomposition, multiplying xj and xk. You apply the Mackey decomposition to the xk factor and write it off as a sum of shifted smaller things. Then these smaller things nicely fit with the transitivity property, and what remains there then are just shifted coset graphs or coset sets in the big group, which by the shift property then give proper sets of coset representatives in the big group. In terms of the picture, in terms of coset graphs, this means in order to multiply xj and xk, well, the xj and the xk involved an inverse, so the multiplication there is opposite to the multiplication of the graphs. But you take a copy of the coset graph for J up here, you take a copy of the coset graph for K there. Then in the first step, you decompose the K coset graph into its constituents by throwing out all the brown edges in this case. Then you provide a copy of the other coset graph for each vertex in the graph over here. You glue them together and then complete the graph according to the presentation of the Coxeter group. So this gives a graphical way of performing the actual multiplication of basis elements of the descent algebra. The product of this guy and that is these two. And it's an example where this is actually a sum of two things. This one-line proof of the formula is from a paper by Bergeron, Howlett and Taylor in 1992, where they do much more. They decompose the descent algebra into principal indecomposable. They exhibit still another basis indexed by the subsets of S. They call it little e's. It's a basis which has the property that each basis element is an idempotent. It shares with the basis of the little x's the property that the radical of the descent algebra is still generated by differences of things labeled by conjugate subsets. And it allows to write down formulas for a complete set of pairwise orthogonal primitive idempotents for the descent algebra as class sums over classes of conjugate subsets of S, which I call shapes, and we will come back to this concept of shapes and how to look at it more closely in a minute. This is a good step towards a Quiver presentation. The primitive idempotents give us the vertices of the Quiver we're looking for. But what's still wanted is a proper presentation of the descent algebra as a quiver with relations. So what do I mean by this? A quiver is simply a directed multigraph Q with vertices V and edges E. The path algebra is the space spanned by all the oriented paths inside the quiver with path concatenation as multiplication. If we denote by curly A subscript L the set of paths of length L, and by straight A subscript L their span, then one can write path algebra as a graded algebra graded by path length, and identify the vertices with the paths of length 0, the edges with paths of length 1. The vertices form a complete set of primitive orthogonal idempotents. That's the nice thing about quiver algebras. They make so many aspects of the representation theory of algebras obvious. This one, for example. In order to write down a quiver presentation, one needs relations, and the relations have to be of the form that they generate an ideal which is admissible. That is, it lies in the square of the radical, in the square of the ideal J generated by all the edges of the quiver. It's a fact that the basic algebra has a quiver presentation. That is a presentation as a path algebra of a uniquely determined quiver modulo some admissible ideal I. Now the quiver, as it says there, is uniquely determined by the algebra with the ideal or the relations that you write down. There is some freedom, some degree of freedom. So that's what I'm aiming at for the descent algebra. Here's an example of a quiver, and this I want to use as the starting point for the construction, and maybe we keep a copy of it over here. This is the Hasse diagram of a finite set S, sorted with respect to reverse inclusion. And if I write down subsets here, I leave out all the interpunctuation, commas and curly braces, so it gets faster. So that's the subset 1, 2, subset 2, 3, 1, 3, 1, 2, 3, and the empty set. And we have paths pointing downwards. Pointing downwards. So this quiver defines a path algebra for any finite set, and here in this example we have the set 1, 2, 3. And I want to keep as an example the Coxeter group of type A3, and there I identify the generating set S with the numbers 1, 2, 3. So I want to apply the construction to the Coxeter group of type A3, the symmetric group on 4 points, which has this set S as its set of Coxeter generators. So here's the plan, general plan. Given a Coxeter group, a finite Coxeter group W with generating set S, we let A be the path algebra of this particular quiver, the quiver given as the Hasse diagram of the set S sorted by reverse inclusion, and I want to present the descent algebra as a quotient of a subalgebra of this path algebra A. So that's a two-step process. First, there's a subalgebra to be exhibited, and then there's some relations to be introduced. The quotient of the subalgebra with respect to the relations will give a presentation of the descent algebra. More precisely, in order to find the subalgebra, I will introduce an action of the free monoid on this set S on the paths, on the set of paths. This action partitions the set of paths into orbits. Call these orbits curly x's. Call the set of orbits curly x. And then look at psi, the subspace spanned by the orbit sums. This is very much similar to the construction of the descent algebra as a subalgebra of the group algebra along the sums over the descent classes, class sums of descent classes. Yeah, this is very much similar. Like then in the descent algebra, these sums form a subalgebra of the path algebra. And that's the subalgebra which I'm looking for. Then where do the relations come from? Well, one can study the action of the free monoid on the paths. It will turn out that each path of length L corresponds to an edge of the action graph on a grade 1 lower, and this correspondence can be used to identify a path of length L with the difference of the endpoints of the edge it corresponds to. That's the relations introduced, the relations identifying paths with differences of endpoints of edges they correspond to. These are relations which are defined on the big algebra A, and if you restrict this to the algebra Xi, the subspace spanned by the orbit sums, it turns out that the resulting algebra is isomorphic to the descent algebra, and this isomorphism can be made very explicit, so that on the basis of that one can then go and construct a quiver and find relations that turn the quiver algebra into the descent algebra. The action. That brings us back to the concept of shapes, which I briefly mentioned earlier. Shapes I call the conjugacy classes of subsets of S. Well, they're not exactly conjugacy classes because they're not complete orbits, but still it's true that the conjugation action of W partitions the power set of S into classes of conjugate elements. These I call shapes. Like in the case of the symmetric group, where everything is labeled by partitions, this of course corresponds to the cycle shapes of elements. I write these classes in square brackets. So J in square brackets is a set of all subsets K of S which are conjugate in W to J. My Coxeter groups are finite, so they have longest elements. Conjugation by the longest element in general, and each parabolic subgroup has its own longest element, permutes the generating set, simply due to the fact that this is the longest element, and it must preserve length. Conjugation with longest element must preserve the length. If one looks at a chain parabolic subgroups, J inside L inside S, then one can consider the product, or if you want, the quotient of two longest elements, Wj times Wl. This is, as a matter of fact, the longest coset representative of Wj in Wl. And its effect on the set J, on the subset J of L, will be that the conjugate of J by D is still a subset of L. On the basis of this simple observation, one can define an action of the free monoid generated by S on the power set of S via the following construction. I declare the image of a subset J under a generator R in S to be the set of all conjugates S by D, where S is an element of J. D is such a longest coset representative constructed as the product of Wj and Wl, where L is the subset J extended by this extra element R. That's the basic observation up here, applied to a situation where the L set has at most one more element than the J set. If this R element already lies inside J, then nothing happens at all there. But if it doesn't lie inside J, then L is a set which is one bigger, and R might or might not move it away. It's a theorem that these little steps suffice to generate the entire shape of J as an orbit under this action. In other words, whenever two subsets of S are conjugate, then this conjugation can be performed via a sequence of such steps, via a sequence of conjugations with longest coset representatives. This action, maybe not as an action of a free monoid, but this action has been used by Howlett in particular to describe the normalizer of a parabolic subgroup, Wj as a semi-direct product, Wj with another subgroup Nj, where Nj actually coincides with the set X, J, K, L, where all the J's, K's, and L's are equal to J, and can conceptually be described as the fundamental group of this S star action of the S star action graph on the shape of J with base point J. Let's call lambda the set of all shapes, capital lambda the set of all shapes of W, and let's study this action in the example of the symmetric group on 4 points. That is in this picture here. Looking at 1, 2, 3, that's the entire set. There's no element R left that I could add to make this set bigger, so this action will have no effect at all on the entire set S, which is clear since S is its only conjugate. Down here, 1, 2, there's exactly one element that I could try and to use and make it bigger. So if I look at 1, 2 and consider the effect of the extra element 3 on this, this means I have to form the big set L, which is 1, 2, 3, the entire set S in that case, and I have to consider the effect of the longest coset representative, that is the product of the longest element in the subgroup generated by 1, 3 times the longest element in the subgroup generated by 1, 2, 3. Longest elements in symmetric groups, they just flip around the order of the generators. So the longest element down here, 1, 2, will flip 1, 2, 2, 2, 1, and that followed by the longest element up here will flip 1, 2, 3, 2, 3, 2, 1, and in particular map 1, 2 to 2, 3 in that order. So this gives rise to an action arrow from 1, 2 to 2, 3 labeled by the generator 3. And if you continue in that fashion, you'll find an arrow leading backwards here, this time labeled by 1. The inverse of 3 is not 3 itself, it's the arrow labeled by 1. It's the element 1 of the free monoid. There will be a loop and 1, 2, 3 labeled by 2, and then there will be various arrows down here conjugating the A1s between themselves. So that's the resulting graph, and obviously whatever you conjugate the empty set with, you get an empty set back, but still there are 3 action loops in this action graph. To distinguish paths in this Hasse diagram from paths that arise in other situations, I want to call them alleys. And in order to talk about them, I want to have a shorthand notation starting with L subscript S as a shorthand for L take away S. One can describe a path in this Hasse diagram as a path starting at some subset L, then L take away some S, L take away S and T, and so on. Or more briefly, as a pair consisting of a starting point, starting set L, and then a sequence of elements ST and so on. That's a pair consisting of a subset L of S and a list, an ordered list of pairwise different elements in L. The action of the free monoid on the set of subsets can then be extended to an action of the free monoid on all parts by simply applying this explicit conjugating element D, which is an element of the Coxeter group, to all the ingredients that are necessary to write down an alley. The image of this path L, ST, and so on under R is L conjugated by D, S conjugated by D, T conjugated by D, and so on, where D is the same element as before, arising as a longest coset representative from extending this subset L by an extra element R. This extends the action of the free monoid on the power set of S to all parts of the paths in the Hasse diagram. And then one can observe that in the action graph on the set of all paths, the vertices of the L grade, that's paths of length L, are in bijection to edges of the action graph on paths of length L minus 1. Through the simple construction that when you start with L, ST and so on, you can take the first entry here, the S, move it, so take it away from the L, passing to L subscript S, and then you know the S element is an element outside the L take away S set, and apply it as an acting element to the shorter path, and that gives you a proper edge in the action graph. If you want to count, this is the action graph we saw earlier. This is the graph on the vertices, on the paths of length 1. And there are as many vertices here as you see edges over here. And so it continues all the way across the paths of length 2. There are as many paths of length 2 as there are proper action edges over here. Paths of length 3, and that's where it stops. There are 6 of them corresponding to the 6 edges in the action graph here. That's an important property of this action. Now, this action partitions the set of all paths into what I call streets. As before, we denote by square brackets the orbit of something. Denote by a in square brackets the orbit of little a under the action of the free monoid, and let curly x be the set of all such orbits, the set of all streets. And as we did it with the original descent algebra, I'm now going, without any notational effort, to identify a class with the sum of its elements. There is a certain danger in doing these things, but it's notationally convenient. So I'll regard A in square brackets as the sum of all the S star conjugates of A in this action. And then, as in the case of the descent algebra, it turns out that when you multiply 2 of these classes inside the big algebra, then you can decompose the resulting product as a combination of such things. The product of 2 streets is a sum of streets, and it can be this sum can be nicely described in terms of groups. If you have an alley from a subset L to a subset L dashed, and a second one from L dashed to L double dashed, so that you can actually multiply them so that they meet at a common point, then the class of A times the class of A dashed can be described as a sum over classes of A times A dashed conjugate by D, where little d runs over a set of double coset representatives of the stabilizer of the A part and the stabilizer of A dashed inside the normalizer complement NL dashed that we met earlier as the fundamental group on the action graph on the power set. It's a description of this product, a description of the product in this algebra in terms of groups. Alternatively, one can use the simple observation that which is true in all path algebras, that paths have what you might want to call prefixes and suffixes. Each path in a path algebra can be uniquely decomposed into edges of the underlying quiver, and in that sense, paths have prefixes. Let's say A dashed is a prefix of a path A. If A can be written as A dash times something in the path algebra, well, let's say that A dashed is a suffix of A if A can be written as something times A dashed inside the path algebra. Using these partial orders, the product of 2 elements of the product of two paths in a path algebra can be described as a double sum over the vertices on the one side and all paths on the other sum, with the property that the two paths to be multiplied must meet in one of these subsets L, and on the other hand, A must be a prefix of the sum of a summand, and A dash must be a suffix. In the case of the path algebra, there will be a unique summand surviving on the right-hand side only, and that only if you can actually multiply these, if the product is defined. The interesting thing here is that the action of the free monoid is compatible with this concept of prefixes and suffixes, so that one can talk about streets being prefixes of one another or suffixes of one another, and one can describe the product of streets in an analogous fashion, where the product of two streets alpha and alpha dashed is a double sum once over all shapes and then once over all streets, with the property that alpha and alpha dashed must have a common shape in the middle so that they can be multiplied. And alpha must be a prefix and alpha dashed a suffix of a resulting alpha dashed. Just that in this case, this is not a trivial formula, because sometimes several summands occur over here. And this prefix business can be nicely described in the form of a rooted forest, or actually two rooted forests living on the same set of roots, namely the partitions of 4, or the shapes of A3 in this case, where, I don't know, prefixes grow down and suffixes grow to the left. And the multiplication of the algebra is completely determined by this graph. It tells us, for example, that in order to multiply this vertex here with a vertex down here, we have to search and find a common shape where they meet, and then we try and extend this rectangle in all possible ways to a complete rectangle, and we find down here the two summands which actually make up the product of these two things. I believe the resulting algebraic psi is actually a path algebra. I've evidence in many examples where it is a path algebra, but I don't see a general reason why it should be. For example, in type A3, where we started with the picture over here and then let the free monoid act on it, forming orbits, it obviously joins vertices which are conjugates of each other together, joins these three into a single and these two into one orbit. On the way, it takes some of the edges and turns them into double edges leading from here to there. But as a path algebra, this algebra actually also needs an extra edge which goes from a subset of size 3 to a subset of size 1. But that's the quiver of which the street algebra of type A3 is a path algebra. So that's the subalgebra construction. Now, for the relations, recall that we have observed that paths of length at least 1 correspond to edges of paths of shorter length in the action graph of the free monoid. Given one such alley, LST and so on, let's denote by delta the difference of the endpoints of the edge it corresponds to. That's the difference of L take away ST and so on, and L take away ST and so on, acted upon by that S element. Then let's impose on the algebra A the relations which identify each alley with its delta image. And let's denote by bars the images of things in the resulting quotient. Then turns out that the quotient of the big path algebra coincides with the quotient of the street algebra modulo the relations only. This quotient has a basis labeled by the subsets of S, being the delta image or the bar images of the proper sets L, the paths of length 0 only. And we've seen this before. The shapes, the sums over such classes form a complete set of pairwise orthogonal primitive idempotents of the quotient algebra. Then, from there on, it's not far to the descent algebra. And this here is the main theorem. If one restricts to the algebra of streets psi, the linear map given by L maps to the element labeled by L in the E basis of Bergeron, Howlett, and Taylor. And this gives a surjective algebra homomorphism to not the descent algebra, but its opposite, which induces a bijection of sets of primitive idempotents that we have singled out before. This means that now every subset curly E of streets defines a quiver in which the elements of this subset, which are attached to unique starting and ending vertices, serve as the edges of the quiver, and also a homomorphism through this map which identifies each edge with an element of the descent algebra, or its opposite. And the question of finding an actual quiver presentation for a given Coxeter group W under these circumstances then reduces to the task of picking a suitable one. That is one such subset E where this homomorphism of course has to be surjective, and you want to be careful that the kernel of the homomorphism gives an admissible ideal. This process can be automated, can be done systematically, and I've implemented this as a program which, for example, in type A, it basically comes down to throwing enough sufficiently many edges of this quiver so that the kernel becomes admissible, and turning around the arrows because there's some opposite involved. Here, in fact, most of the edges disappear. These pairs of edges become singletons, and that's the result for type A3, which is a straight line and two singleton sets and doesn't involve any relations. There are other examples. I've said already the quiver for type A has been known for some time and has been more properly proved by Schocker a few years ago. Saliola has used the hyperplane arrangement and the face monoid that comes with it to describe the quiver in type B, which is of a slightly different nature. I've computed quivers and relations for all the exceptional types. The relations for type AN are under investigation by a student of mine, Marcus Bishop, and a general description of relations, in particular the entire quiver for Coxeter groups of type DN, are completely open questions. In type E6, the quiver, or the non-trivial part of the quiver, looks like this, where I've distinguished short edges from long edges through the colors. There are two relations on this quiver, one involving this vertex here. I use A111 as a shorthand for A1 times A1 times A1. We go from here to A41 to E6, and from here to D5 to E6, and it doesn't quite say that these two paths are the same, but up to a factor 2 there. And another relation which actually originates in type A5 starts with A11, A21, and then it goes either A31 to A5 or A4 to A5, the sum of these two paths. Well, this is, of course, subject to the chosen homomorphism. The relations are not by no means canonical. In other types, in types where W0 is central, the picture falls apart into two halves. E7 illustrates that there can be multiple, 4 in this case, edges between two quivers. E8 can be computed, and more information is available at these points. Thank you very much.
So, could you, maybe you said this already, but the conjecture that the street algebra is a path algebra?
Yeah.
Would that have, what's the relationship between that and the main theorem?
It's not, the main theorem doesn't depend on it. But it would serve as an explanation why this approach works in the end. Because in a sense, talking about presentations, if you have a presentation of a big object and you pass to a sub-object, then it might be difficult to find a presentation for that. While passing to quotients, you can easily find presentations there. And in this two-step process, passing through the sub-algebra, I think in some sense one is lucky that still enough structure is maintained so that the subsequent quotient construction allows for a quiver presentation to be built.
And so you can verify that the street algebra is a path algebra in
Up to rank 8.
Up to rank 8, okay.
So I'm convinced it is one, but I don't see why.
Any other questions? If not, let's thank the speaker again.